This is a photo that was actually taken in my backyard. There's Dave and I were with 3 graduate students, Eamon Orhan, Matt Overland, and Ilka Yildirim. Dave and I were in the same department for 16 years. Our offices were just down the hallway from each other. It was always a great pleasure to, Dave's door was always open. I would constantly pop into his office and talk about anything. It was always a great pleasure when Dave popped into my office. One of the things I find more and more, however, is that of course I miss one-on-one conversations with Dave, but more and more I find I miss being with Dave in groups of our students. It was really in group meetings with a bunch of students that in many ways Dave's greatest qualities really showed. He was really, really smart and really, really quick, and you saw that it's quite obvious. He was really also kind and generous, and he would spend a lot of time on your ideas, and I kind of want to emphasize that a little bit. Dave and I were interested in a lot of things. We were interested in visual perception, of course, but we were also interested in the broader topic of multisensory perception. We were interested in the relationship between perception and cognition. So we thought a lot about visual perception, multisensory perception with respect to things like sensory motor integration and learning and memory. And actually, the next speaker, Chris, is going to talk about some of the things we did in the intersection of perception and memory. What I thought I would do today is to tell you about 2 projects. Just to follow up on something that Paul just said, Dave was really adamant that you really shouldn't be studying kind of visual tasks in the abstract. You really had to study vision or multisensory perception in really near ecological context. And in many cases, not all, in many cases that involve looking at perception in sensory motor context. And so you'll see a bit of that today. The first project I want to talk about is the project that Dave and I did together. It was on perceptual learning, particularly we looked at cue reliability and cue recalibration. The second project, actually Dave and I didn't do together, but in some ways he played an important role. As I mentioned and other people have mentioned, Dave loved talking about science. The exceptional thing about Dave was he loved not only talking about his science, but he loved talking about your science too. And Dave could spend hours talking about your science, because if Dave saw any kind of hand waving in your arguments or anything you were doing, you weren't leaving that room. And Dave absolutely, he drilled down, he got to rock bottom. It was first principles all the way. And you didn't get away with anything. And wow, that was a great service both to me and also to the students who really saw, wow, what it meant to really be a serious scientist. And that's just by example, it was a great lesson. So for this second project, I want to talk about generalization from perception to motor production. As I said, this was a project that actually Dave wasn't involved in, but it was only through subsequent conversations with Dave that I later came to realize a little bit more about the implications of that work for perceptual learning. And for me, this illustrates one of the most important points about Dave, and I guess I've already alluded to this. My brother and I, we often argue about who was the world's greatest basketball player. And I often say, well, it was Magic Johnson. Because Magic Johnson, his real talent was he made everybody around him a better basketball player. And that's often how I feel about Dave. Dave made everybody else around him a better scientist. And in some ways, I don't know, to the rest of us, that was his greatest gift. Okay, the first project is on Q reliability and Q recalibration. This is a project that Dave and I did with Joe Atkins. Joe is a graduate student in the lab, and a faculty member at Colby College. Dave and I were interested in visual learning, perceptual learning, and particularly the idea, I think first put forward by Bishop Berkeley in 1709, that perceptual learning can occur because, in this context, touch educates vision. But that Berkeley meant that perception of visual space results from associations between visual sensations and sensations of touch and motor movement. In our particular project, we asked the following question. Can observers adapt their interpretations of a stereo cue on the basis of consistencies and inconsistencies between depth from stereo and depth from haptic percepts? In this experiment, the visual stimuli were, there were scenes of two surfaces. So there was a narrow surface which was relatively close to you, and behind that was a bit of a wider surface. Subjects viewed these scenes head-on, so you got an orthogonal view, and things were set up so that really stereo was the only reliable visual cue to the depth between the two surfaces. So you can kind of see that here really on the left-hand panel. There's a green surface which is relatively narrow and closer to you, and behind it is a blue surface a little bit further away from you. Subjects saw these surfaces in a head-mounted display, but in addition to seeing these two surfaces, subjects could also reach out and grasp the surfaces. So this subject, her thumb and her index finger are really connected to two kind of robot arms. This is a haptic force feedback device known as a phantom. And when the subject's fingers are touching the two surfaces, these robot arms will apply forces so that the subject cannot close her fingers any further, mimicking the sensations the subject would receive as if her fingers really are up against the two surfaces. So that's another cue to the distance, the depth between the two surfaces. In the experiment, subjects made the following judgment. Is the width of the front surface greater or less than the depth between the two surfaces? And sometimes subjects did this just based on visual cues, other times they used both visual and haptic cues. So this experiment had 4 stages. First, subjects performed consistent cue training trials. By consistent cue, I mean that the depth, that is the distance between the two surfaces, indicated by vision and indicated by haptics, were one and the same. Then subjects performed pre-test trials. These were visual-only trials. Then subjects performed inconsistent cue training trials. Here we had an offset between depth from vision and depth from haptics. I'll say more about that in a second. And then there were post-test trials. Again, post-test trials were like visual, pre-test trials, they were visual-only trials. So we're looking to see if, based on the inconsistent cue training trials, people would recalibrate their interpretations of the visual cue. And we would be able to see that by comparing their performances on pre-test trials versus post-test trials. Note that this environment gives us independent control of depth from stereo versus depth from haptics. So on those trials with inconsistent cues, we made the reaching distance greater than the viewing distance by 60 millimeters. However, the binocular disparities were consistent with both reaching and viewing distances. The net result of all of this is that we scaled the depth between the front and the rear surfaces such that depth indicated by haptics was greater than depth indicated by stereo. And our prediction was that based on these inconsistent cue training trials, that subjects will adapt their depth from stereo estimates so that these estimates become more similar to their depth of haptics estimates. And that's exactly what we found. This is data just from one of the subjects. If you look at the graph on the right, the horizontal axis gives the depth minus the width. So that's the distance between the two surfaces minus the width of the front surface. The vertical axis gives the probability that this subject responded that the depth is greater than the width. The solid line is a psychometric function fit to this subject's data on the pre-test trials, and the dotted line is for the post-test trials. And what you can see, there's a rather substantial shift. This is a subject who, yes, recalibrated her depth from stereo estimates. And moreover, this recalibration is in the direction of the depth from haptic estimates. It wasn't just this subject, it was actually all of the subjects in the experiment. So in this graph, the vertical axis gives the post-test point of subjective equality minus the pre-test point of subjective equality. This is just a way of saying, is there a shift in the psychometric function from pre-test to post-test? And there's a large shift for all of the subjects. So from this we can conclude that yes, actually Bishop Berkeley was right. One of the ways we can learn about how to interpret our visual environments is by looking for discrepancies between, let's say, vision, and in this case haptics, and recalibrating our visual interpretations so that they become more similar with our haptic interpretation, just like Bishop Berkeley would have speculated. So that was cool. That was a nice way of looking at perceptual learning and seeing how learning relates to another sensory modality, in this case haptics. For this second project, as I mentioned, the second project I want to talk about, Dave was not a collaborator on this project, but it was only through conversations with Dave later on that I kind of realized the implications of what we actually did, and now I like this work better than I did at the time. So good, let me tell you about that. This is work that I did in collaboration with Dan Megan and Dick Aslan. Dan was a postdoc working with Dick and I. Dick's a faculty member in our department. We were interested in whether people would show generalization from perception to motor production. So the experiment had 3 stages. First, subjects performed motor production tests. So there were 2 motor production tests. I'll tell you about them in a second. Then subjects underwent perceptual training, and then finally, again, they performed these motor production tests. And we're looking to see, will perceptual training influence their motor production performances? And we'll be able to see that by comparing their performances on the motor production test before visual training or before perceptual training with after perceptual training. The motor production task was to produce 2 finger taps separated by a target temporal interval. In task 1, the target interval was 300 milliseconds. In task 2, the target interval was 500 milliseconds. And subjects got feedback. We showed them the actual temporal interval. The perceptual training task was an auditory temporal interval duration discrimination task, where temporal intervals were indicated by 2 auditory tones. So here on each trial, subjects heard 2 intervals, what I'm going to call one interval I'll call the standard, the other the comparison. And they judged which one was longer. So the standard was always a fixed duration, but the comparison, the duration of the comparison interval changed based on an adaptive staircase. For half the subjects, I'll call that half group 1, the standard interval was always 300 milliseconds. For the other half of the subjects, group 2, the standard interval was 500 milliseconds. Our prediction was that subjects will show more motor improvement when the temporal requirements of the perceptual and motor tasks are were identical. That is, that subjects trained to perceptually discriminate the 300 millisecond interval from other intervals will show the most improvement on producing 300 millisecond intervals. And an analogous statement holds for the 500 millisecond. And that's exactly what we found. So the vertical axis here is showing you the reduction, percent reduction in motor timing variability. So on this motor production task, people show some variance in their performances. And we're looking at the reduction in that variance from pre-test to post-test. The two bars on the left, those are for the group 1 subjects. They were trained on the perceptual task with the 300 millisecond standard. And what you can see is they show the most motor improvement when producing the 300 millisecond interval. And for the two bars on the right, those are the subjects in group 2. So they were perceptually trained to discriminate the 500 millisecond interval. And they show the greatest motor improvement when producing a 500 millisecond interval. So that is, subjects showed more motor improvement when the temporal requirements of the perceptual and motor tasks were identical. So yes, we really did find generalization from perceptual training to motor production. Well, good. At the time I thought, that's kind of moderately interesting. But Dave thought that was a cool result, and we had a lot of conversations, actually many years after this work, about this, the implications of this kind of experiment. In particular, my lab in the past few years has been interested in modality invariance and cross-modal transfer of knowledge. So what is cross-modal transfer of knowledge? This occurs when you acquire knowledge about the environment through the through one sensory modality. However, you apply the acquired knowledge when the environment is sensed through a different sensory modality. For example, we've shown that if you learn to visually categorize a novel set of objects, you can also often categorize the same and similar objects when they are grasped but not seen. Well, to us, to Dave and I and other people that we've been working with, cross-modal transfer and transfer from perception to motor production seem like closely related phenomena. They're both forms of generalization from seemingly very different situations. Let's say a visual task to a haptic task, or from a perceptual task to a motor production task. Both of these suggest the existence of amodal representations, modality-independent representations that are not tied specifically to vision, not tied specifically to haptics, not tied to auditory temporal intervals, not tied to motor production, but something that abstracts over these particular tasks. And if so, then experiments on transfer from perception to motor production will have implications for perceptual learning. Many people in this room have studied perceptual learning, and a fairly frequent finding is that studies report that perceptual learning is often stimulus specific. So you learn about the specific stimuli on which you're trained, but that what you learn does not necessarily transfer to novel stimuli. However, note that cross-modal transfer of knowledge is, by definition, not stimulus-specific. If you're trained on visual stimuli, but you generalize that to haptic stimuli, well, that's not stimulus-specific learning. And so that raises the question, when is generalization narrow and when is it broad? In our experiment on transfer from perceptual training to motor production, we found that subjects simultaneously generalized both narrowly and broadly. So their generalization was narrow in the sense that they showed transfer of learning, or their transfer of learning was better for the trained temporal interval. However, their generalization was also at the same time quite broad. They showed transfer of learning from perception to motor production. And so that raises the question, are people biased toward cross-modal transfer? And our hypothesis is that the answer is yes, that perhaps cross-modal transfer has a privileged status. That is, people are biased toward generalizing cross-modally, even under circumstances in which they simultaneously fail to generalize, or they generalize narrowly, along other dimensions. So this was a hypothesis that Dave and I just recently started talking about, and we thought about ways of testing that hypothesis. So that's something that I need to do now, but it's only something that I would know to do now through lots of conversations with Dave, in which we thought about work really that I and others had done, but he got really interested in, and he thought hard about, and realized these other implications. And so for me, this is just an illustration, one of many possible illustrations of how Dave made me better, just like he made many of the other people in our department, our graduate students and other people, through conversations with him, through his absolute rigor and absolute determination to get to the bottom. He just made us better scientists. So, thank you.
So we have a minute or two for either a question or a reflection on your interactions with Dave.